Okay, welcome to the second part of this tutorial. In this tutorial, we're going to add some more attributes on the terrain, which we will use later again. So we'll start off a little bit simple. So let's just start with a facet node. We'll connect that, visualize it, and put it on post-compute normals. As you might notice, it doesn't really change how the scene looks in the viewport, but if you enable point normals, you actually do see that the normals are now generated. If we go back to the file cache, you can actually see these green arrows instead, which basically are the intrinsic vertex normals. But if we middle mouse button click, we don't see any normal information in this list. So because we want it to be sure that it's point normals in our case, we're just going to generate them using the facet node. Alternatively, you could initialize them like this: vn equals vn. I believe this should work too. Yeah, it does. This only actually works if the normals don't exist yet. Otherwise, it will just use the normals from the input. But with facet, it always will regenerate them if you enable the post-compute or pre-compute. Okay, so we're going to start with a wrangle. And this wrangle is to calculate the slope. And to get the slope, we're actually going to use a dot product. And we're going to use the normal that we generated with the facet node. So we want the slope that is between 0 and 1. And luckily, a dot product does mostly that, especially in our case. So we can create a dot product between the n and the up, the world up in this case. So how does that actually look? Let's add a visualizer node. Let's add the attributes. And in this case, we want it to be a ramped attribute. There we go. And I would prefer okay. Nope. Let's keep it at y2 right there. Okay, but as we can see right now, our slope is actually inverted. So because you can see that the right side is red and the left side is white. So we can simply fix that by using 1 minus. And now the slope should be correct. Okay, for our tutorial, we're actually going to use the slope between 0 and 1. But if you actually want the slope to be in degrees instead, you can do that too. And we're going to use another property of the dot product for this. Because what the dot product actually generates is the cosine of the angle between the two vectors. So if we use the a cosine of what we just generated, we now have the angle in radians. So that would be between 0 and 5. half a pi, I think. Doesn't work like this in this case. So that would be, say, 1.5 very roughly. No, that's a bit. Oh. Seems that it doesn't really scale in the same way. Yeah, because the slope is not interpolated in the same way if you use the angle version versus the dot product, of course. So right now it's in radians, but if you want it in degrees, you can simply cast it using the degrees function as well. So now we can get the slope between 0 and 20. Are those sensible values? Let's check. So if we go to our slope values in the geometry spreadsheet, yeah, so right now, okay, yeah, that's why. Because right now we don't need to add 1 minus it, I think. So yeah, it does get very steep. No, we still need the 1 minus. Okay, there we go. Catch me lying. Okay, there we go. So yeah, you can see that the interpolation is slightly different because this is compensated for the fact that a angle is spherically interpolated, and right now it's linearly interpolated. But this will suffice for what we're trying to do. Okay, so on to some more complicated wrangling now. So let's call this get slope. What we also want for our terrain is the ambient occlusion. And Houdini has some tools to bake the ambient occlusion using mantra and stuff like that. But in our case, we're just going to write all the ambient occlusion directly in the subcontext. And in case you're not really familiar with like ambient occlusion, what it actually is, it's basically from every point or every point on the surface, you're sending out rays along its normal and normals that are slightly deviating from the same normal. And the amount of rays that hit other geometry versus the amount of rays that are free, so to speak, basically generate the value of your ambient occlusion. So let's set up a very basic ambient occlusion first, which uses just one ray. I'm just going to make our network view a little bit larger. Okay. And also, in this case, I'm going to add a color node instead of a visualizer node, because a color node I trust to always update dynamically. So right now, there's no values yet, so everything will be black. But let's start. So we can basically specify the ambient occlusion by checking if it intersects, like the raycast function is called intersect. This is the first input, using the position as the starting point, and then the normal as the direction. And in the case of the intersect function, we also need two output vectors, which is the out position and the out UV. In our case, we're not going to really use them, but they are required for the function to work. Okay. So right now we see a very speckled result. And that's for two reasons. The first reason is because right now we're only using one ray. And the other reason is that the intercept function actually returns the primitive number that is hit by the ray. So if you, with certain functions, you can use that information together with the UVs to actually get interpolated data at the position where the ray hits. But if it doesn't hit anything at all, it equals -1. So we can just say equals -1. Okay, but we actually want the opposite. So we're going to say is not equal to -1. Okay, so you don't see the difference, but if you go to the geometry spreadsheet, now the ambient occlusion, at the start, yes, it's either 0 or 1. And if I remove this, it will go to crazy heights. Basically the amount of primitives that the geometry has. Okay. So to improve the ambient occlusion, we actually need to first do one minor thing. And that is because of how the intercept function works. If you start the ray on the geometry itself, there is a chance that it will hit itself. So we're just going to add another vector here, which we're just going to call P, and P will be equal to the current position. And then we're just going to offset the position by just plus equals by the normal times a very small amount. And then instead of PP, here we're going to use P. And now it should be completely black, because none of the points should hit anything except in some really rare cases. It's also a good point to note. Let's start adding that. So we also need to control how far from the current position we want to check for any nearby meshes. So I'm going to say max occlusion range. Well, I'm going to say max range equals CHF, which is channel float. You can also use CH. That will generally create a float, but it can also do other parameters. But to be sure that it is going to be a float, I'm using CHF. And one of the advantages of wrangling like this is if you specify it like this and you press this button, it will automatically generate the attribute for you. So now we can actually multiply the normal by this value. And if we now start to make the range much longer, we might get some, yes. some self-intersection. So rays starting from this position actually hit this geometry here. So that actually starts to generate some ambient occlusion. Also going to disable the lighting and the wireframe. Well, we do need the wireframe. But yeah, so now we can actually start improving the ambient occlusion. And the main way to do that from here is to actually increase the amount of rays that we send out per point. So we're going to specify the amount of samples using CHI, which is channel integer. And again, we can, oh, I forgot the semicolon. There we go. The amount of samples, let's put it at 4. And now we actually need to generate our loop. I'm also going to actually change the near clipping plane a little bit. Yes, so now I can zoom closer to the mesh without it disappearing. Okay, so we now have the total amount of samples, and we also need hit samples, which will start at 0. So now what we're going to do is create a for loop. Integer I equals 0 till I is no longer smaller than the amount of samples, and every iteration we're going to add 1. So let's put that in a loop. And now every time we're going to do a raycast. And we're going to actually increase the hit samples every time the intersect function returns something that is not equal to -1. And what we can do then is divide the amount of hit samples by the total amount of samples, and that should give us a ratio. But right now there's still no change, and that is because right now every ray is actually in the same direction. So we need to fix that too. And also because I guess I'll leave this for later so I can actually demonstrate it. Okay, so for every iteration in the loop, we actually want to generate a slightly different randomized normal. But we still need to make sure that the normals are generally in the same direction as the original normal. And to do that, we're going to just let the wrangle generate a matrix for us. So matrix z to n equals dihedral 0, 0, 1, which is z, to n. Okay. So, and now we're going to add a sample direction as well. So vector sample there equals a vector ren e, and this will actually generate a vector that is between 0 and 1. So if I start using this instead of the normal here, probably won't generate a very good looking result. Yeah, there's some random spikes. I mean, yeah, so in the positive direction right now, following X, we do get some hits. But we actually need to do two things. First, we need to make sure that this value also can go negative. So we're going to use fit 0, 1, because right now these values are between 0 and 1. And we want to transform it to -1, -1, 0, and 1, 1, 1. Wait, yes, that should work. Because we want these values to be ranging between -1 in x to 1 in x, -1 in y to +1 in y, and from 0 and 1 in the z-axis. So if I use that, probably will still generate a one-sided result. And that is because right now the vector is not yet aligned with the normal vector. But that's quite simple as soon as you actually have a matrix to do so. So we can just say sample dir times equals c to n. Now we should start to get something that gets closer to an Iterate occlusion. Okay, but right now we can still see that it is a very binary result. And that is because we're dividing two integers by each other to generate a float. So we can simply, instead of making it an integer, we can just make it a float. And hopefully that will do the trick. Yes, that actually does do the trick. Okay, because right now we're dividing a float by an integer, which will generate a float without any clamping. Okay, but right now it actually is generating the same pattern for every point. So if we would add the point number, it would now generate a more noisy, randomized effect. That's very random. Seems let's increase the amount of samples. Yeah, you can see that it quickly starts to be slower and slower. So if I would add another one to this, then multiply this by a large number, how does that look? No, that's still not right. So in the rand function, that's why. No, that should be correct. Because normally I would do I plus 1 times a random number plus pt_num plus 1 times an arbitrary number. And that should do the trick. Because we're specifying that we want a vector out of the rand function in this case. Okay. Yes, I think it actually does work, but the amount of samples that we're using is just, I think I know. The amount of maximum inclusion range is just way too high right now. So if you just set this to, say, 20, we probably get a more refined result. Yeah, okay. So now we can clearly start to see the occluded areas. Okay, so we just made a very basic ambient occlusion. But as we can see, it's quite noisy. And we do want the, I mean, we could go back to the same pattern for every point. But instead, we could also actually make our pattern sampling more uniformly. And that's actually like one of the advantages, I would say, of using wrangles like this. And that is if you like know what you want to do, but you do not exactly know how to do it in terms of code, there's a very high chance that someone else already coded it at some point. And usually people are very willing to share their coding on sites like Stack Overflow. So after some minor Googling, I just copied the node, by the way. I found this page. And we can see here, like, this is sort of close to the result that we have. And this is much closer to what we would like. So basically, Rory, together with the help of some of these commenters, actually gave us this nice piece of code that we can use. Right now, it's not in the language of X, but we can fix that. So we're just going to copy paste this here at the top. And in our case, we actually want the function to return a vector. We're going to call it cosine sample hemisphere. And we're going to use the U1 and U2 the same way. For vex, constant floats are not really what we need in this case. We're just going to use generic floats. And we're going to return a vector, which we actually need to specify using the set function in this case. And also in vex, almost all function calls start with a lowercase letter. So that's also an easy fix. And then there is one, the constant of pi, we can actually specify like this in our code. Okay, so now we have a function that using two float inputs can generate a sample. Okay, so if you actually want to use that, we need to have two inputs. But right now we only have one input, which is I. So what we're just going to do is add another encapsulated for loop, j equals 0, j until it's no longer smaller than samples, j plus plus. I'm just going to put the entire code in the loop one step deeper. And then instead of having this random function here, we can say that the sample direction equals cosine sample hemisphere I, let's cast it to a float, divided by samples, because this function, after reading in the article and looking at the code, expects a number between 0 and 1. We're just going to divide it by samples, comma float j divided by samples. Then we still need to rotate it towards the normal. And then there's one thing we still need to do, because we're actually using the square of the samples right now. So we need to divide it by samples times samples. And because we're using the square of the samples right now, I also want to use less samples overall. So if I would go back to 4 samples, I'm just going to quickly save just to be sure, and put the update mode back into auto update. Okay, so I got something in the code somewhere. Okay, like when I was trying this earlier to copy this code, actually middle mouse button clicking on the code to see what was wrong actually did manage to crash Houdini. So I'm just going to quickly look at the reference and see why it doesn't compute. Let's make it a small c. Okay, that doesn't do anything. Let's unlock also to be sure. So if I would copy over the same contents, with that cook. Okay, so yes, that does change. I'm going to quickly check what the actual difference is between the code. I still don't manage to spot the actual difference. Yeah, it seems pretty much identical. So maybe there's just some hidden okay, it actually did manage to. Okay, so I believe the spaces that were used in the example code on the website actually do not conform well with facts right now. Oh, I'm just going to replace them again with. Okay, so there we go. So yeah, if you directly copy over the code from the website, that's actually why it's not functioning well. I'm guessing it's some special hidden characters that are there in the code. Oh yeah, so we still need to actually specify the sample there is a vector. And now we're starting to cook again. Hopefully this will soon actually generate the result. Okay. So let's actually re-add the color again. Yes, okay. So now we have a quite uniform ambient occlusion. And there is, well, of course, we can improve it simply by increasing the amount of samples that we use. But I also want to quickly show what the actual difference is. So I'm just going to copy over the example that I have prepared. So here I generate 2 points just to show that these don't have any normals right now. But in the first example we generated was random samples like this. So all in the positive direction, but randomized. And if I would actually increase the amount of samples, you would see it would be pretty arbitrary in which direction they would go. Also, if you use a completely normal random vector, it's actually safer to normalize the vector before you actually multiply it again by the maximum occlusion range. The uniform sampling actually doesn't have that problem because the function generates a vector that is already normalized, because how cosine and sine actually generate the length of the vector. But if you look at this, it actually is a very nice uniformly spaced set of directions. And there's actually one difference with the samples that we have right now, because we didn't add the -1 there yet. So without the -1, it actually doesn't sample the direction directly perpendicular to the normal. So if we go back to the ambient occlusion, press G again to focus the camera. If I would add brackets around samples and subtract 1, it should generate more ambient occlusion, because right now the chance that something will hit at least one of the rays is much higher than before. Okay, so there is 2 more things that we want to do. Just if you are running on like an older PC, this is actually quite an old machine right now. But if you want to have a good result in terms of ambient occlusion without using many rays, you can also just smooth the result. So if we use a smooth node, smooth it like this. There we go. Yeah. So now we have a slightly blurred. And if we want it to be even smoother, we can just go back to 1. And if we would apply it to the random ambient occlusion, it would look more like this. Oh, yeah, so it's still recomputing the wrangle again, because every time you copy a wrangle node, it will, well, first of all nodes that you copy will basically recook But in the case of a wrangle node, it also recooks if you change the name. And that is because inside the wrangle node, the function is actually generated using the name of the node. And because the name of the function changes, it has to recook. But yeah, you can see that using the random direction, it's still noisy even after smoothing. So let's keep going with the uniform ambient occlusion. So I'm going to put it in manual update mode so it doesn't recook. Ambient occlusion uniform. Copy, paste. Random. Okay, so now it probably will recook. Yeah, it does. Okay, there we go. Okay, and there's actually also one other thing I want to point out that you have to remember if you're using a smooth function. If we go to the geometry spreadsheet, still the other node was selected, I guess. If we check the range, the ambient occlusion, okay, there we go. So it goes between 0 and 875 right now. And in the smooth, it should still generally do that, but still goes between 0. But now it actually, because it's all blurred, the maximum is actually reduced. But if we would increase the filter quality, it tries to maintain more of the contrast into the source. And in certain cases, that actually might go outside of the original range. So to prevent that from happening, I'm just going to add a safety here, which will be ambient occlusion equals clamp ambient occlusion 0 between 0 and 1. Clamp amp. Okay, so now it should always be between 0 and 1, no matter how much filtering we use. Also be quite careful with using high numbers of filtering because it greatly increases the amount of time that the smooth will take, and memory, or video card by default, I suppose, because the smooth soap uses OpenCL. Okay. So right now we're actually in unlit mode. I would go back to lit mode. We have this really strong specular, which I'm not really fond of in this case. We could actually bother to generate a shader to fix that like in the long run. But for the purposes of this tutorial, we can actually work in unlit mode. But since we already have the ambient occlusion, we might as well add it into the actual color of the map. So let's do just that. So if we use the vector of the color diffuse and multiply it by the ambient occlusion, it will probably return the reversed result. Yes. So now we can start to see difference between adding and without adding the ambient occlusion. But you can also slightly increase the contrast by using a fit function. So if we would remap the ambient occlusion for, at least for the purposes of the color, like this, contrast should apparently decrease. Yes. Need to be like this. Okay, there we go. So basically, using this fit function, it basically doubles the amount of ambient occlusion that we have. Because whenever the ambient occlusion is 0.5 in the input, it will now be 1. But it will never go over 1 because fit also automatically clamps the value. There's also efit, which will keep the value unclamped, but in our case we actually do want the value to be clamped. So multiply ambient occlusion with CD. Okay, also let's clean up our nodes a little bit, because we're not really using these anymore. We can get rid of those. We don't need this example anymore. And also in the previous tutorial, we didn't really ended up using this part. So I'm actually going to use Ctrl B to make the network view full screen. I'm going to select the entire nodes chain and hold the A key and then drag my cursor downwards. That will align them nicely. And then I'm just going to press on the subnet button. And that will just package up the first part of the tutorial. So we're just going to call this generate heightfield. And then for the second part of the tutorial, can do the same again. Generate terrain patterns. Okay. In this case, we don't need to cache our result just yet. We'll add some more functionality and then cache it again in the next part of the tutorial. Okay, hope to see you then.